Thank you very much. So when I thought about what I should speak about, I realized that, one of my main projects in recent times, you see, we both were with Andre at Northeastern, but somehow in the recent semesters we were kind of crisscrossing. Okay, last spring I was away, he was here. Last fall he was away, I was here. Now I'm away. So I never had the opportunity to tell him about this. So I'll tell to you instead about this project. I apologize because it's a commutative algebra. Okay, so everything will be commutative for a long while, and so let me tell you what it's about. So first I give you, it's about free resolutions over commutative rings, but then there's some representation theory coming in. So first I give some background. Then I give kind of state the problem, and then I'll kind of describe the approach, and then we switch to talk about something else, Weinberg representations, and then I'll show you how it connects. So that should be the okay. So we deal with basically R will usually denote an Assyrian ring, commutative, and we'll talk about free resolution. So complexes F1, F0, Fi are free modules of finite rank. So I'll employ this notation that the differentials will be di's, and they will have a rank of di is Ri. So I assume also it's a free resolution, so I assume also that F is acyclic, meaning it has only H0, that is non-zero. So it's a resolution of some module. And that's right. So the first thing one needs to know, just as a background, is, how, if you see such a complex, how do you prove that such a thing is, for example, acyclic? So there's this, basic results of Buchsbaum and Eisenbach. This is the exactness criterion. Which tells you that this F is acyclic if and only if two things happen. First of all, a rank for each I, if I look at the rank of the free module Fi, it will be Ri plus 1. So that's the criterion you would get if you would have vector spaces over the field. Obviously, complex of vector spaces would be exact in that spot if rank of this map plus rank of this map is dimension of that space. So that's really, you repeat that. And the second is something like this. First of all, I define the rank of a map in the following way. Well, if I fix basis in my Fi's, then each di is just a matrix of elements in the ring. So then we can look at the minors. So rank Ri is the size of maximal non-vanishing minors of di, treated as a matrix. Of course, it does not depend on the choice of basis. And then we have those ideas I of di that you can associate to this complex, which are exactly the ideas generated by those maximal non-vanishing minors. Okay, so the second thing in the criterion is that for each I, depth, so codimension of this I of di is at least I. So it means whatever. Well, if you think of your spectrum of your ring as being some variety, the subvariety defined by vanishing of those minors, it has to have codimension bigger or equal than I. Okay, but now the problem I'm interested in is the following. We would like to fix the format, so we fix the ranks of everything. We of course will assume this equality because we want to have a chance to have an acyclic complex in that format, and we are asking whether there exists a kind of universal object of that kind. Well, not quite universal, but somehow almost universal. So let me formulate this. So the question does there exist one would like to have an Noetherian. So first of all, we fix the format. So this n tuple R1, Rn, and maybe sometimes I'll call it R underlined. Does there exist a Noetherian ring R generic and an acyclic, that's important, acyclic complex F generic over R generic of format R, such that for every pair GS, where S is also Noetherian and G is acyclic of format R, there exists a homomorphism, non-unique. That's the point. We do not require a unique homomorphism, but I'll explain a little bit why. R generic to S, such that this G can be obtained from this F generic by a change of basis. Okay, so that's a natural question. Somehow to look for this kind of universal object. And well, the point, I think this question, whether such a thing exists, was posed by Hochster, but it goes back to the classical example, which goes back actually to Hilbert. So let me just tell you what I have in mind. So let's take the example, which is Hilbert-Birch. So let's look at the resolutions of the type Rn-1 Rnr. So it means we take the format 1 n-1 as our format. So Hilbert already noticed, so we have D2 and D1. So in such situation over, well, Hilbert noticed over polynomial ring, but Birch generalized to arbitrary situation. Then basically, you see I have this D2 is a n by n-1 matrix. So I can denote by delta I the n-1 times n-1 minor of D2, which I obtain when I skip the ith row. And then it turns out that there exists actually a non-zero divisor in R such that, well, let's maybe denote the generators by x1, xn. So I pick my basis, and well, this is D2, this is a matrix, such that xi is, well, -1 to the I guess, a delta I. So what it means that every such ideal that is actually projected dimension 1, when you look at the image of that map, is determinantal. Okay, so this has a lot of applications in algebraic geometry. Like every Cohen-Macaulay scheme of codimension 2 is determinantal. So this is okay, Hilbert-Birch theorem. But you see, we can now rephrase it in this language in the following way. What I do, I take my R generic to be z xi yij, where maybe I put capital X and capital Y. This would be now variables. I'm thinking of the matrix D2 as being, with my choice of basis, as the matrix Yij. And actually another element A, another variable A. And then I divide by the relations, you know, y times x times y is 0, and then by those relations star. xi equals -1 to the I a delta I. And of course, over this ring, then I'll have a complex F generic, which will be just given by the cosets of x's and y's, because I impose the relations that the composition is 0. And in fact, then it turns out this F generic is acyclic. So one has to prove it, but that's not so difficult. F generic is acyclic, and somehow, well, so this means that it's a universal object, because now, and actually in this case the map will be unique, because, well, it's really on the board, everything that's needed for that. So our map, of course, will take capital X, Y, and A to small x and y and a, and we are done. So that's kind of a model case. And then, well, once I think Hochster asked this question whether such a thing exists, and I think it was very quickly settled in the late 70s by Hochster and Kuhnecke. For n equals to 2, one can always do it. Okay, so Hochster, Kuhnecke. Okay, if n equals to 2, the answer is yes, and there's an explicit construction that I'll kind of on the way I'll maybe explain. So today I'll try to explain what actually happens for n equals 3, and the situation seems to be much more interesting. All right, so let me maybe now say a little bit about one generalization of this Hilbert-Birch theorem, again by Buxbaum and Eisenbach, to arbitrary format, before we then go to the... So in fact, you see, if we have now F arbitrary, there's something called first structure theorem. Again, Buxbaum, Eisenbach. Basically tells you, you see, we have those maximal minors of rank Ri for each of those maximal non-vanishing minors for rank Ri. And well, they proved the following, which kind of generalizes Hilbert-Birch theorem. It explains somehow what's going on, why do we have this A. They proved for general formats the following thing, that so I have now F is general. They proved that there exists a sequence of maps AI from the ring to wedge Ri Fi minus 1, such that the following factorization occurs. Basically, see what happens here is kind of not difficult to understand. If you have the map of rank Ri, then it's Ri's X0 power, the map given by Ri minors, has to be of rank 1, right? The image, if it would be vector spaces, the image would be a vector space of rank Ri. So in the X0 power, it would be a point in the Grassmannian, really. And so what you take here, so you know the matrix of rank 1 usually factors, right, through the one-dimensional space. So such factorizations occur here. Basically, what you can do, you have AI here and here. Well, you can here write AI plus 1 star, because you can treat this as being wedge Ri plus 1 Fi star. So kind of numbers match up. You can write AI plus 1 here. So okay, well, I didn't tell you what An is, and An is just so equals to wedge Rn on the last differential. So the point is that there's a unique sequence of such maps from R to this wedge Ri, you know, such that those factorizations occur. So you see, if you take n equals to 2, you get, for example, immediately this. There will be a map from R to R, this A. And so really, the AIs are like Plücker coordinates of the image, you could say, of the I's differential. So that's somehow where things stood. And so in the 80s, I mean, I was working on this problem for a long time, and I kind of got halfway, and somehow, but recently I was able to complete it. So let me explain what the strategy was here, because the strategy is quite, yeah. So let me make a note that first of all, a non-Noetherian R generic always exists. Okay, so why? It's actually quite easy to explain. You see, what you do, you can certainly construct something that would be called a generic complex. You just take for a given format, you take a bunch of variables for all the matrices, independent variables, right? Kind of like we started in this n equals 2 case. Then you impose the conditions on ranks. Ranks should be Ri, so some minors vanish. Then you impose a condition on composition 0, and you got a complex. But of course, the problem will be that, well, you have a complex of this variety, but it will not be acyclic. But what you can do when you have this complex now, you are over an Ethereum ring, so what you can do, you can start killing the cycles. So, you know, each homology module is finally generated. So what you do if you see some cycle, Fi plus 1, some bunch of cycles coming from some free module X, then since in every realization that will be acyclic, those cycles have to be boundaries, right? So if you want to construct this generic ring, you have to add really basically other set of matrix coefficients with, you know, so here's your cycle C. So here you add some kind of matrix coefficient map entries of some matrix P, so, and you put the relations as the differential di plus 1 times P is C. And you basically do it for each homology group. You get a bigger complex. Then, okay, again, it will not be acyclic, but then you keep doing it. You do it countably many times, and then it's not difficult to see that after you do it countably many times, your complex will have to be acyclic because, you know, you get this sequence of rings, R1, R2, Rn. So you see, this whole procedure is kind of funny. You keep the complex fixed. These are your kind of original generic complex, but you change the ring, okay, and make it bigger and bigger until it gets to be acyclic. Now, so, well, the point is you see that if you do it countably many times, if you have any cycle in the kind of limit of those rings, of course, it's a finite thing, so it will really come from the level Rn. And if it was a cycle from the level Rn, it is killed on the n plus first level. That's more or less what happens. I mean, the rest is just. So anyway, non-Ethereum thing always exists, but of course this construction is kind of like a general nonsense thing, you know, and it doesn't really tell you much because it's non-unique, and you know, you would like to really do it in a more kind of nice way, maybe as symmetric as possible, and just see whether you can construct such an object explicitly, because then you could hope for some applications. Okay, so that's kind of the goal. And so let me now rephrase the problem a little bit. So I had this Buchholz-Eisenbach criterion, you see. So I look at this, I start with this FC, is generic complex. So I'm over this ring RC, and actually, I talked about this first structure theorem. I can also, what I can do, I can add, actually change C to A. So I take generic complex and I add those coefficients, matrix coefficients of AI, of those maps AI, which have to exist for any acyclic complex. That's what this first structure theorem says. Now they satisfy a lot of relations. I will not make them explicit, but this can be worked out very, very explicitly. What happens, which relations AI have to satisfy together with the differentials DI. For example, they satisfy Plucker relations, okay, because they were this, you know, Plucker coordinates of this image. So you can really construct this ring RA quite explicitly. And it's a very nice ring. By the way, I mean, it's very close to quivers, right? We are looking really, we start with generic complex, so it means we start with some orbit of the AN quiver, right? Which is a very simple orbit even. All compositions are 0. So those orbits, for example, are spherical, okay? So, and in fact, it turns out that the ring RA, you see here, all the constructions are equivariant. So of course we have this group acting on everything, G, which is, you know, GLF1 cross GLFN. And in fact, you know, RA, you can decompose to the representation of this group, and this ring is multiplicity free. So you can really kind of deal with it. Okay, you can deal with it. And well, it's also very nice. It's called Macaulay rational singularities, whatever you can imagine. So that's a nice ring. So this is kind of a starting point. So the strategy is to start with this ring and start killing cycles. Okay. And it turns out, a long time ago, I was working on that for quite intensely for n equals 3, because, well, that was kind of the first case, and it's also so interesting for other reasons. And then I could arrive at some explicit cycle. So let's specialize now for n equals 3. So we just have F3, F2, F1, F0. And you see what we'll be doing, we'll be changing the ring. So I take it over the ring RA. So it means I took, 3 generic matrices, rank conditions, etc., added coefficients A, added a bunch of relations they satisfy. I have this complex. And if I look at this complex here, and I look at the, how far it is from the Buchsbaum-Eisenbach criterion, I get that ranks are okay, and then the depths are 1, 2, and 2. So in fact, by the way, if I would do the same for the lengths n equals to 2, that will be the generic ring that Hochster and Huneker constructed. If S3 would be 0, I would just get the generic ring. So you see here now the point is I have this D3. The point is I want to basically raise the depth of this from 2 to 3. That's really kind of how the problem can be rephrased. Well, and working with this RA, since it's multiplicity free, it's not difficult to see. So there will be only first homology that will be non-zero. And it's not difficult to work out what its cycles are generated by. And there's some map, funny map, but I'll explain it. So over RA, H1 of this complex, I call it FA, is generated by well, you have the map from F3, no, maybe wedge R1 plus 1, F1. Okay, I mean, maybe it's not clear, but let me just tell you what happens. Let's specialize here into the case R1 equals to 1. Then you see what happens. I have here R F1. So I have something that should be a resolution of some ideal. So I have some map, some matrix coefficients x1, xn. So obviously you have causal relations. They have to satisfy causal relations. So if you take the map from H2 F1 to F1 that gives causal relations, this will consist of cycles. So you have to kill. You have to add coefficients B. So that's right. So this is kind of a generalization. There's a map from here to here given by maximal minus of z, and by Laplace expansion composition is 0. It's really nothing fancy. So you have this factorization P1 of this map that I would call, I don't know, well, F. Okay, so you have this factorization P1, and here you come to the start appreciating difficulty, because now which actually distinguishes the case n equals 2 from n equals 3 and higher cases, because you see, if n would be equal to 2, the lifting of P1 would be unique. Because in every realization which gives you a cyclic complex, this map would be injective, so the lifting would be unique. And in fact, what happens for n equals to 2 is that when you start with generic complex, basically, in order to construct the generic ring, you just add fractions, okay? However, if, well, here the lifting is not unique because, of course, I can always add any map from here to here. So if I want to now add those scalars and or relations, those variables and all relations they satisfy, I have to kind of take into account this this non-uniqueness. But what it means, if I want a universal object, I have to kind of lift in democratic way. So the way I kind of was trying to deal with this is that, okay, I'll just lift, and you see there will be an action of the additive group of this home from here to here, big space, I don't know, this wedge R1 plus 1 F1 star tensor F3, will be acting on my bigger ring. So the strategy is to kind of preserve this symmetry. So we add P1, and then from RA we get the ring R1, and there is additive group that I call L1, which is wedge R1 plus 1 F1 tensor F3 star acting on it. So I can think also about abelian Lie algebra acting. Okay, so then of course your variety is not spherical. Things get quite hairy. But then, well, for a long time I thought that that's everything. But then it turned out that it's not. And actually over R1, one can spot another cycle. However, this will be a cycle in kind of not exactly this complex, but kind of a companion complex. What I can do, I can write a companion complex which will really be kind of like F. You see, I take using basically tensoring my maps with, I don't know, F3, or this here it will be, this will be coming from D3. This also will be coming from D3 kind of tensors with F2. And then I here take S2 F1. So this is like second symmetric pair. By the way, here I'm working already for some time. When I talk about representations here, I'm really working over the field of complex numbers. So anyway, it turns out that there's this very interesting cycle. Now you see, this is a companion complex, I say, because if you look at the ideas of minors, for that complex and for that complex, they have the same support. So somehow, if you will know, this will be acyclic basically precisely if and only if this will be acyclic. This depth of these three minors will be, well, will be the same in both cases. So it turns out you have this funny thing. You have the map from wedge 4, F1, which actually, oh, of course, here I am in the case, again, R1 equals 1. So I have this, new cycle. And this is really, you see, kind of like second symmetric power of this map P1, okay? By a tensor construction, if you take and restrict to some summands, you will get a map like this. It turns out to be a cycle, so you have the map P2. And then, so again, has this what I call defect. So there's this L2, which will be now, in this case, wedge 4 F1 tensor wedge 2 F3 star. This strange thing, you see. And there's an analog for arbitrary length. So you see, now I will have this situation. I have my ring RA, R1. I added P1 here. Well, you know, I have to do some things at each stage. I mean, I'm kind of skipping a lot here. I have R2. And there's this action of this additive group L1 here and the additive group of L2 here, or maybe the action of abelian Lie algebra. And remember, in the case R1 equals to 1, I get here wedge 2 F1 tensor F3 star. And here I get wedge 4 F1 tensor wedge 2 F3 star. So now the question is, what could be, you know, how could I describe maybe this ring over that ring? I would like to have some kind of nice group of transformations acting. And well, it's not so difficult to see what happens. Namely, well, you see this L2 occurs in the second exterior power of L1. If you know representation theory, how it decomposes the tensor product of, you know, two copies like that. So I also have the bracket, skew-symmetric bracket from wedge 2 L1 onto L2. So I can define a two-step nilpotent algebra, L1 plus L2, L2, which is L1 plus L2. And actually, that's what will be acting, okay, on that ring, such that this will be the fixed point, more or less. So, well, after I did that, of course, you can ask if there are other cycles, and then suddenly, what happened that from this you could actually construct infinitely many cycles, potentially infinitely many cycles. And that's where I kind of got really kind of, well, disappointed a long time ago and thought, gee, I mean, now, you know, it's completely a hopeless problem. So how do you construct the, it turns out that, okay, what you can do, you can basically, well, start constructing from this L2, you know, it's a graded Lie algebra, okay? But so it's a normal Lie algebra which is graded. It's not like a Z2 graded algebra or anything. Just normal graded Z graded Lie algebra, actually N graded. And then, you know, if you have such algebra, you can look at the universal graded central extension, okay, by H2. So in fact, and you start keeping doing that, you know, infinitely many times. So in fact, you can construct then basically inductively, if you know something about Lie homology, basically you construct, so we construct inductively Ln by well, there's the usual Koszul differential going from wedge 3L to wedge 2L. I will not write it down. And if you look at the n plus first graded component, then you will see here that you here only see Li's and Lj's for ij smaller than Ln plus 1. So you can construct this as a co-kernel. And this gives you a nice sequence of L's. And then L, which is direct sum of Li's, is a Lie algebra. And in fact, in this case, it turns out that it's just quadratic relations. It's a universal algebra on as many variables as you need here. And you just have quadratic relations, which you can already see from L2. That's kind of an accident, but you just have just quadratic relations. And it turns out that I could construct the whole. In fact, you see, one has to kind of switch again. And you see, since I have this choice of a complex, I was using companion complex to define this P2 that may be not good enough. So the canonical way to do it somehow is to change your cycle, so to speak. And actually, since we want to raise the depth from 2 to 3 for this ideal I of D3, the minors of this map D3, so we look at the Koszul complex. So K will be a Koszul complex on all maximal minors I of D3 over the rings that we need, you know, some ring Ri. I'm adding those coefficients of those pi's. So I have K0, K1, maybe K0, K1, K2, K3. That's the beginning of the Koszul complex. And one knows in commutative algebra that an ideal has depth 3 precisely when this part of Koszul complex is acyclic. So really, I could start killing the homology in this Koszul complex. It will be somehow more canonical. And then it turns out that indeed what you can do, and basically somehow this diagram fits with the diagram of those Ln's. So you have basically diagram of Ln's. Now I have to change my cycles because, well, P1 and P2 were kind of killing cycles in this complex F in this companion complex, but I can find the similar cycles which kind of sit in the corresponding place in the Koszul complex. So I have the cycles Pi tilde, and now you see if I constructed some of them, starting with P1 and P2, that has to be done explicitly, then here I will have something, you know, this would be the cycles Pi tilde going from my Li star to my K1. So here I get basically summation Pi wedge Pj tilde. Here I get summation Pi wedge Pj wedge Pk. And then this will define for me, since this will have to be seen every realization, every specialization of an Arthusian ring where my complex F was acyclic, so my IDC will have depth 2, so this will be acyclic, so then I have factorization Pn plus 1, Pn tilde. So I construct this horrible sequence of those structure theorems, and I know that every time I add, the dimension goes up. So you see now a natural question appears. Well, for small formats, maybe there are only finitely many L's. So then we have a chance to construct an Arthusian ring. If, however, the number of L's is infinite, then we'll never finish, and the ring just will not be an Arthusian. Okay? But the question was, and that's what got me stuck, what is the algebra L? Because if it doesn't make any sense, it's just way too complicated. And in fact, already a long time ago, I kind of had, you know, some way of proving that if such thing holds, that the ring is generic. In fact, I could write some family of complexes over the enveloping algebra of this L, infinite family of complexes, and if I would know that in some prescribed places it would be acyclic, I would know that this is a generic ring. I avoid here a lot of things, but okay, so then I got stuck, and I didn't know what to do with this. So remember now, we can forget about almost anything here, except remembering that in the case where the rank R1 was equal to 1, then there was this nice algebra that we had So R1 equals to 1. We had L1 to be wedge 2F1 tensor F3 star. And then L2 equals wedge 4F1 tensor wedge 2F star, F3 star. And well, then we could have quadratic relations. So then, and you see then, the point is really, the whole point is that this algebra can be recognized in a very different context, okay? So like much later, I got interested in the gradings of on Lie algebras and the work of Winberg, so-called Winberg representations, which are somehow important because they are irreducible representations of well, semi-reductive groups which have finite domain orbits, and actually they exhaust like most of those representations. So you know, what are Winberg representations? Winberg representations. Well, you start with, for example, G to be a simple Lie algebra. Well, it could be also semi-simple, but it doesn't matter. And you distinguish, look at the root alpha I, some simple root. And so the way I encode it is, you know, I could, for example, I encode it by, well, simple Lie algebra will have some Dynkin diagram. And then there will be a simple root, which is my, well, black or white node, depends how you look at it. Anyway, so the filled node, let's say. And then, you know, you have this grading. Basically, you can now take G, gets a Z grading, where Gi, well, we put Cartan in G0. And then basically Gi is the span of all the roots alpha. Well, maybe I want alpha k. So we want all the roots alpha such that if I write now alpha as a combination of simple roots, I will see I alpha k. All right, so then you see, yeah, at some point actually I was working out this example that's on the board over there. And you see that's a kind of a nice example. So you have G of E6, and this has dimension 78. If you look in Bourbaki tables, you have this root, and then you know also that, you know, if you take the highest root of E6, it will have coefficient 2 here. So this algebra will only go from, in this grading, from G minus 2 to G2. Then also in such situation, one knows what will be my G0. G0 will be all roots orthogonal to alpha, plus one guy that you have to have, because which kind of centralizes, I think, this G0, because your maximal Cartan algebra got smaller. So, okay, if you look at Cartan algebra of G and this G0, which will be the Lie algebra, corresponding actually to the root system that you have when you skip the filled node. And so then G0, one knows that in this case is SL2 cross SL5 cross, well, the abelian algebra C. Because you see I have A1 root system, A4, so that's my G0. And then one always knows that these are dual to each other. And then you work out this grading. I mean, you know, you can just count the roots and see how simple roots act on roots. I mean, you know, it's not that difficult. You will see that G1, in this case, will be C2 tensor wedge 2 C5. Okay, I'm thinking about, you know, C5 is corresponding to this part, and C2 corresponding to this root system. So this exhausts, you know, so here I have what? 24, 25 plus 3, 28. And this will exhaust 10. This will exhaust also 10, because it has to be dual. So something is funny, no? 20. 2 times 10 is 20, right? So, okay, so we got 68, so we need 10. So it means I need something of dimension 5 here and here. And well, if you look at what happens, you know, there has to be also, of course, a bracket. The bracket preserves the grading, so I have to have a map from wedge to G1 to G2. And then you have, you will see very quickly, and also there are many other ways of seeing it, that wedge 2, C2 tends to wedge 4, C5. So at that point, actually, yeah, when I was doing those exercises, this was kind of this aha moment that, you know, I noticed I've seen this algebra before, right? Maybe a long time before. So that's right. So this turns out that's how the pattern shows up. And so here, let me tell you what's the general pattern for resolutions of length 3 and what happens here. So here's a kind of description of the result. And somehow, if you realize these connections, then everything falls into place. Basically, you know, you need some results, you go to Kumar's book, and you just find all the results in Kumar's book in the proper places, okay? You really don't have to do anything at that point. So here's the result. So I look at my 3 ranks. I have ranks R3, R2, R1. And I associate with a triple PQR, which is R1 plus 1, maybe R2 minus 1, R3 plus 1. So maybe I do R1, R2, R3. And then you associate with a graph TPQR. So here you take P minus 1 nodes, here you do Q minus 1 nodes, and here you do R minus 1 nodes. And then you pick this root on the R node, the root next to the center here. And then the proposition is that that this defect algebra L, well, it really depended on the format R, is now you see, okay, this is not a Dynkin graph in general. Now you already kind of can predict what my answer will be to when the Noetherian ring exists. But, but of course, in such case, you have a Kac-moody Lie algebra, right? And it has a Z grading, okay? Just as it's infinite. So it's just the positive part of this, you know, TPQR. And that's it. Well, not that's it, because the point is, that's right. So then I had those, you know, like mysterious complexes, okay, which were complexes of 3 modules, and that turned out to be parts of the BGG resolution, parabolic BGG resolution for that case. So the theorem falls, okay. So here's the result then is that, so first of all, for each format, R3, R1, R2, R3, there exists R generic, which with a multiplicity free action well, you see what multiplicity free action. Notice, well, to construct my algebra L, I only use the odd part of the complex, F1 and F3. So I still have GLF2 cross GLF0, and that's actually how you analyze everything. You can analyze some spectral sequences that are behind it, because you can always decompose everything with respect to GLF2 cross GLF0. So you have multiplicity free action of GLF0 cross GLF2 cross this G of this TPQR. So that's 1. And 2, notice also, I should, well, okay. Yeah, so that's right. It's a commutative ring, but with the action some kind of spherical variety for this huge thing. Okay. And second, of course, now, also, well, I didn't tell you what those complexes were, but you see, the point is that R generic. These are complex of the complex that give you that the ring is actually generic. That's the complex exists. These are complexes of this UL modules, but the ring components, kind of parts that go into the ring itself, are the co-kernels. So actually, that's why the whole ring has this, additional actions. There's a hidden symmetry here. Okay, that my GLF1 cross GLF3 actions that I would get from here. In fact, this ring exhibits bigger symmetry, and this can be used then to prove that basically the lattice of weights is kind of the same as the lattice of weights for this RA, but somehow just you have to take bigger representation. And second, of course, then R generic is Noetherian if and only if TPQR is Dynkin. So at least this is a uniform way of constructing such rings. Okay, so that's now I'm not claiming, that could happen by accident. Also, I don't believe it. I'm not claiming this for other formats. Some other crazy generic ring does not exist. But if you want to preserve the symmetry and you want to be democratic, that's the only way. So really, I think it probably shouldn't be. Well, I mean, it should be possible to prove that these are the only cases. But anyway, in those Dynkin cases, you can actually do it, and that's right. So there's the main result, and now you see, actually, the result is pretty explicit. It's not. It seems like because that Jesus, I add so many generators, I don't know, what to do here. But actually, if you have this multiplicity-free action, this result is explicit. So let me show you, for example, what happens for like in the smallest case. Let's just I just tell you basically what I'll do. So I'll look at the case of 1 n minus 1 1. Okay, so this is a resolution of the type R Rn Rnr. Well, a lot of you know about Buchs-Eisenbach theorem for Gorenstein ideals, right? Of course, this is a different case. I'm not assuming that this thing is perfect. Okay. However, notice that if I take this format, what will be my thing here? Okay, my thing here will be this. So the format tells you, and the Weinberg approach tells you, that you better look at the second extra power of Cn. So it points out to the representation that where the Pfaffians are. So it's not an accident, and I'll show you why it's not an accident. Okay, so let me show, So what I'll do, I'll just construct for you some cycles very naively, okay? And then I kind of show you that really they come. See, in this case, my big algebra is the orthogonal algebra, okay? So basically, I'll show you how you can see that somehow the cycles can be put together into half spinor representations. So you can see that really they come from the. So okay. So suppose I have, I don't know anything. Yes. That's right. It's always the guy that touches the node, right? Yeah.
Does it also say what's going to be in G2, G3?
No. For this, you need, in hyperbolic cases, you need formulas, and there's kind of the whole area of people working on hyperbolic systems, and it's a science. Yeah, that's right. I should also point out that it tells you exactly, you see the G1 is exactly whatever F3 tensor wedge R1 plus 1 F1, okay? Always, from the Weinberg prescription. Yeah, for other GIs, you have to work. And also, even, I would say, let me just not to get like overly optimistic. If you look at the guy of type E8 of finite type, okay, you look at where the generators are in the lattice. So one of them has dimension 600 million something, okay. So I mean, it won't be easy probably to exhibit, all the finite cases. But some small finite cases you can actually, like I will show you in a moment, you can interpret all the cycles and what the generators are. So here, I'm assuming I have a cyclic complex over an Noetherian ring R, and I will produce for you a family of cycles, and then basically they exactly correspond to the extra generators you have to add. Okay, so that's the point. So okay, so I have some, x1, xn. So what I can do always, of course, I can, let's call this maybe G1. So I can compare to the Koszul complex again, the same thing. So I can do G1, wedge 2 G1, wedge 3 G1, wedge 4 G1, etc. So I'll have the comparison map equals, and then since that guy is supposed to be acyclic, it will lift. right? So you see from this I'll get, maybe I call it now G2. My G3 will be R. So I get, two cycles P1 prime. So I will see, I don't know, G2 tensor wedge 2 G1 here, and I will see also wedge 3 G1. I'm probably skipping some stars, right? But it doesn't matter. So I see that one and that one. So these are kind of the extra things that we see. Okay, so that's the first step. But now I can do the following. My complex is acyclic, so this composition is 0. But this means, since this map is supposed to be injective, I'm of a cyclic complex, that this composition is 0. Okay, so I get a map from wedge 4 G1 to R, which is well, so this composition is 0. So what I should say, that's right. So here I get 0. So this means I can construct the next thing. I have 0 R G2 G1 R. So I start again with Koszul complex. But now I write here wedge 4 G1, wedge 5 G1, wedge 6 G1, etc. And now here will be the map that you get from that guy when you contract wedge 3 G1. So here is kind of P1 prime tilde, I would write. And then it turns out, that, well, this is a complex because this composition is 0, basically. So you can lift again, okay? So you get P2 and P2 prime. You can lift because this guy in this realization has to be cyclic. Because so we get P2, P2 prime. So I get G2 tensor wedge 4 G star. Sorry, wedge 4 G1, and I get wedge 5 G1. And then you can continue. So in fact, you see you get G2 tensor one half spinor and the other half spinor. And if you see the formulas that I got there, you get exactly those representations in exact places. Okay, so you see in this, I didn't, I have the my R generic. I have a decomposition as over some alpha and lambda, and here you have some weights V lambda 1 G0, tensor V lambda 2 G2, tensor GL F0, GL F2, tensor V alpha 3 of this G of TPQR. So if I look inside of my lattice, what accompanies, I don't know, the trivial representation of F2, I will see just, the half spinor, and I see also F2 times other half spinor. So somehow it fits really perfectly. In other finite cases, one can give interpretation to some generators as concrete cycles, but then, as I said, it becomes a little hairy. But but at least the result is there. Also, I should point out one more last thing. One can look at the symmetry of this whole thing, because when you have the graph TPQR, then you have this so-called triality, right? You can now, permute your root, right? And see which formats correspond, to which formats it corresponds, because then those formats should be somehow linked. Now here we enter the phase of speculation. Well, I mean, I can tell you what the formats are, but it suggests, that something nice is happening. Now, see, I'm not assuming here this is a perfect idea, this is a perfect complex. In fact, the next step that I would like to do is to kind of do the same thing for perfect complexes, where I just take the complex F, and I'll be killing cycles in F and F star. But at the same time, so to speak. But the point is now permuting the PQR. So if you just permute P and R, then from the format of the complex F, you go to the complex of the format of the complex F dual. So somehow, that's right. So the format of F is of finite type, so to speak. It's has an Noetherian ring if and only if the format of F star have Noetherian ring. But so that already suggests that maybe it should be possible to somehow generalize it to Cohen-Macaulay case, because at least both of them have Noetherian rings at the same time. But much more interesting is what happens when you switch P and Q, because this points to the linkage. I mean, one of the reasons why one hoped always that the resolution of length 3 have a nice structure, and that somehow this case is somehow special, is that there's this linkage thing, you know. So, well, basically you have some resolution Rm, Rp, RQR, say for an ideal. What you do, so the resolution of some ideal, then you can take 3 generators which form a regular sequence. You have a Koszul complex, you know, you compare, and you have equal here, and then you take the dual of the cone and you get another resolution, right? And you get resolution of somehow another ideal, but somehow the sum of all those dimensions stays the same. So you kind of stay in the same family, and you can do it many, many times. So this suggests that, you know, that somehow there's some structure there. So this turns out that somehow this is somewhat related to the linkage, but slightly more general thing. So if you switch P and Q, okay, I should not write, I should ST, sorry, because it has nothing to do with this PQR. You see, when you have what you do here, if you want to get from one format to another, Rm, Rs, Rt, Ru, then you can kind of take comparison map from Buchsbaum rim complex. Ru, Ru plus 2, Ru plus 2, Ru, whatever. You just pick submatrix whose maximal minus already generates something of depth 3, and then so you have equality here. Again, you take the dual of the cone, then you get the format that you get when you switch P and Q. So it suggests if one can do it for Cohen-Macaulay for perfect complexes, then I hope it would be explanation of, you know, what happens in the linkage. Okay, but anyway, so that's where it is right now, and that's, I think, everything I have to say. Well, for Windberg stuff, you can use as many as you want. Then you get the this G1 will be reducible. So they always have finite element orbits. But I think then these do not exhaust. You know, even for one dot, they do not actually exhaust all representations with finite element orbits. There are a few exceptions that are listed, right? There are just a few more. But just very, very few. There's one series, I think, and just 1 or 2. Yeah, that's right. But of course, if you have more black dots, then there are many, many more. Like you will not get all the quivers, for example. I think with, well, I mean, yeah, that's right. If you take AN quiver, you put many black dots, you know, you get actually equioriented AN, but you do not get, I think, other ANs. Okay, so. No. Here is just use TPQR in this particular black dot. Yeah, just that's right. So yeah, maybe, you know, I think this Kac-moody world is so big that there are many, many other things actually hidden there. Yeah, but yes. That's what Cox just asked me. Someone.
Nagata construction of invariants and not finally generated was based on things like that. So you take a Cox ring of the tensor surface or flow up of vector space, you get also typically non-Noetherian rings.
That's right. Okay, there's a definite connection with Nagata counterexample, because actually when you raise the depth from 1 to 2, you get the strict transform, and that's a difficult one has to avoid. I mean, here. So only after you see the hidden symmetry, you know, that there's a bigger group acting on the string, you see that's Noetherian, because that's right. Even intermediate stages when I was working before, you were never sure you were getting Noetherian rings up to strict transform, you know. So that's right. I think that's right. When I was at UMass, also Stevelev was immediately gave me his paper. Yeah, that's right. Yeah. Okay. Tony, yeah.
Yeah, I just wanted to ask. You can finite star dating diagram gave you an authority condition, but what about affine? Can you say something special about affine case?
Not yet, but you see, I would actually hope to use the affine type to actually prove that you cannot construct the Noetherian ring in any way somehow. Because the idea would be, I think, to look at those formats and to kind of construct a family of resolutions that really are different somehow. And then, you know, that would be my hope. Yeah, for affine, of course, one can control the GIs because they are periodic. So at least you know what the GIs are. But I didn't get to that. Right now I'm going through finite type cases trying to see which generators I can identify. It takes so that's where I'm. Yeah, but I'm sure affine will be next. That's right, yeah. Yes.
Suppose I want to fix the Hilbert function of a graded module of three variables. So there'll be different formats that correspond to it. And so if I want to understand the irreducible components of the family, does this help?
It's very far from this. Notice that even for n equals to 2, actually that's kind of a sad part of the story, if the generic ring for other formats, it really does not have really that many applications so far, because I think the scheme is singular. So, home, whatever, from the schema to the scheme is, it's not so, But, So I wouldn't no, it's much too subtle, the components of the Hilbert scheme. Yeah.
All right. Let's thank Jerzy again.
Okay, I also happen to be one of the organizers, so I wanted to really thank you for coming for this conference, and I think the beauty of Andrei mathematics came really through. And that's right. And I would like to thank in particular Ben, who did 95% of the work organizing the conference. Yes, thank you very much.